So now we're gonna jump into our 3.2, which is our domain and range. And we only have two learning objectives here, being able to find the domain of a function defined by an equation, and then graphing piecewise defined functions, which I think people are usually very intimidated by this second objective, but it's literally just knowing the pieces of different functions and then putting it all together onto a coordinate plane. So it's quite straightforward, and I'll make it quite easy for you. Okay. Our first objective, finding the domain of a function defined by an equation. So I just want to run through very briefly interval notation because say 90% of the time we're going to be using interval notation in order to write out our domain and ranges of certain functions. And you guys have been educated on it a lot in Math 190, but it's the summer, people forget things. So I'll just very subtly touch upon it. The parentheses represent the sort of endpoints not being included. So an example, let's say we had our domain represented all values from 2 to 10. This on a number line would indicate all values between 2 and 10, but not including 2 and not including 10, including all numbers, whether it's 2.001 or 2.156, all the way up to 9.9998. Whereas the hard brackets that you see down here will include those numbers. So if we have a domain that represents values between 2 and 10 and including 2 and 10, we're now looking on a number line where instead of it being an open circle, it's a closed circle at both 2 and 10 because we're including those two values as well in our domain. And that first and two, that number one and number two bullet points is just saying, okay, how do we write it? It's just as if you were to read a book from left to right, smallest to largest. You're always putting that smaller number first, and then that larger number last. So these are all the different possibilities. You do not have to memorize this. It's literally just saying what I touched upon over here with these two examples, but they also indicate the inequalities. And instead of using open and closed circles, they just used parentheses and hard brackets. The parenthesis is just a synonym for an open circle, whereas the hard bracket is a synonym for a closed circle. And I can write that up here so you could see both options. And then from an inequality standpoint, again, you know, the mouth is towards the greater value. So X is greater than A here, whereas the point is a smaller, X is less than A. And then if there's a line underneath it, then it's including that. So any line underneath, you're dealing with closed circles. X is greater than or equal to A, and so on and so forth. So now we're into our first example for this section where we're asked to find the domain of a function as a set of ordered pairs. Anytime you're dealing with sets, it's very, very straightforward. All you have to do is look at your X values. If there are any X values repeated, you just write that value once. Lucky for us, there are no x values repeated, so we just have to write all of the numbers that I highlighted. And there we have it. This is our domain for this set. Our range would just be all of our possible y values. And I'll write down our definition of domain informally over here, equals all possible x values. Example 2, now we're asked to find the domain of this polynomial that we're given, which is x squared minus 1. This is where those toolkit functions really come handy, because we know that x squared is just our parabola over here. But then that minus 1 tells us that we have a transformation taking place, just like you guys learned in Math 190. And that transformation is a vertical shift down 1 unit. We'll deal with transformations a lot more in our section 3.5 today. This is sort of like the preview to that. And so if we're shifting this x squared down 1 unit, our new vertex is at 0, -1. But does that affect our domain? Does this affect all of our possible x values that are being represented? How many people think yes? How many people think no? It doesn't, right? There are no restrictions. Our domain is, we're representing all of our x values regardless. Our domain of x squared is all real numbers. Our domain of x squared minus 1 is all real numbers. Nothing is being excluded. So you can write your domain as all real numbers using that script R, but in interval notation, what is this? Negative infinity all the way to infinity. And infinity, because it's a symbol to represent that all real numbers are being represented as our domain, we use soft brackets. Infinity is not a number, it's a symbol to represent the numbers keep going on forever. So you don't want to put in hard brackets. It's always soft. So our domain here, negative infinity to infinity. I know it doesn't ask us this, but it's important to know how to find your range too, even though it's less common. Our range, again, definition, is all of your possible y values. And so if we're looking at x squared minus 1, which is what we have in purple on that graph, what are all of our possible y values? What's the smallest y value possible? Yeah, and is it going to be a hard bracket or a soft bracket? Yeah, because we're including that -1. And then do we have any restrictions for the maximum? No, it keeps on going. So what's that second one going to be? Yeah, exactly. Soft bracket. And then we're done. So this is just notes on if you're given a function written in an equation form that includes a fraction, how do we find the domain? And so uh, that goes back to me always saying, do we have any restrictions? And if there is a denominator, aka fractions have numerators and denominators, then what value can never be in the denominator? Why can't 0 be in the denominator? Yeah, exactly. It would make the fraction undefined. And we don't want undefined values a part of our domain. So that's what this is formally saying. We want to make sure that any x value that makes our denominator equal to 0 is excluded from our domain. This is known as a restriction. Any questions on this? They also did mention the whole roots and even indices. And that's important to note too, because that's another potential restriction. It doesn't have to be a fraction for this to be the case. But if you ever see a square root, what can never be underneath a square root sign? As long as we're in the real number system. Exactly. And so we want to make sure that anything underneath a square root or an even root index is positive or 0. Anything under, and we'll practice these, square root or even root index is positive or equal to 0. Another restriction. So anytime we're finding domains, these are the two restrictions we look for. What makes the denominator undefined, and what values of x will make underneath that even root index negative. And we'll end on this example, and then I'll give you guys a nice 20-minute break. So we're asked to find the domain of the following function. Again, domain. What are our two restrictions? Undefined denominators and negative under radicals. So lucky for us, do we have any radicals here? No. So not needed for this problem. But do we have a fraction and do we have a denominator? Yep, so we need to utilize that first one. We really just have to hone in on the denominator. We don't need the numerator at all. And we make sure, okay, Our denominator can't be 0, so what makes it equal to 0? Just add x to both sides, and so when x is equal to 2, right, if we plugged in 2 here, we'd get 2 minus 2, which equals 0, and that's a restriction. So this is our only restriction. Which means we need to exclude this from our domain. So from a number line perspective, all other numbers are fair game, except that value of 2. So open circle at 2, everything else is good. How do we write that in interval notation? All values from negative infinity to 2, soft bracket because we're not including 2, union all values from 2 to positive infinity. And we're done. So this is just a slide on if you're given a function written in equation form that has an even root index, then you just want to find your restrictions on what makes underneath that radical negative, and you want to exclude that from your domain. So we'll be practicing examples that include radicals that have even roots now. And so now in this example 4, we're looking at f of x is equal to the square root of 7 minus x. And again, we do not want this to be negative. So our domain is going to be all values that are positive or equal to 0. So greater than or equal to 0. And then we just solve for x. So we can add x to both sides. And essentially we're looking at 7 is greater than or equal to x. I always like to have the variable on the left-hand side. So I'm just going to rewrite it as x is less than or equal to 7. And that these both mean the same thing. The point towards the x and the point towards the x stays exactly the same. So this is our domain, but now we want to write this in interval notation. What does this look like on a number line? We're looking at all values that are less than or equal to 7. So we're including 7 and we're looking at all values less than 7. So from interval notation perspective, this is just negative infinity all the way up to 7, hard bracket. And this is our domain. Questions at all? No. Yeah. Good question. So remember back to our restrictions when it comes to domain. We want underneath this radical, aka our even root index, to be positive or equal to 0. Because anything negative, the square root of -4 ends up into the imaginary world. That ends up being 2i, which isn't a real number. And we're staying in the real number system. So that greater than or equal to stems from positive or equal to 0. It's greater than or equal to 0. Right. Another way to identify domain and range is just simply by looking at a graph. If you're given the graph, it's very, very straightforward because your domain is just all of your possible x values. So if all of your x's, there's no arrows at the end of this, well, there's no arrow here, but there's an arrow here. And so this tells us that the smallest domain is at -5, and the largest one keeps on going forever. So our domain, all of our possible x values here, we're including that -5, so it's going to be a hard bracket, and then it shoots all the way to infinity because we have no bound on this right-hand side. But then our range, we're looking at all of our possible y values, and we look from up to down or down to up. Again, there's no restriction on the minimum, so we have a negative infinity, but we have a maximum because it only hits up to +5 and includes that number 5, so it's a hard bracket. It's much easier to identify domain and range from a graphical standpoint because we just see everything. We don't have to do any algebra to get to our solutions. Now let's look at another example where we're dealing with a graph. And so we have find the domain and range of this function. Our domain, again, all of our possible x values. There's an open circle here, so we're not including that -3 in the domain, which means it's going to be a soft bracket. And then it goes all the way up to 1, and there's a closed circle at 1, so we're actually going to include 1, so it's going to be a hard bracket. Bless you. Whereas our range, now we're looking from up to down or down to up, we have our smallest value is -4, it's closed circle, so we're going to include it, -4 hard bracket. And then it goes all the way up to our x-axis, which is 0, but it's open circle, so we have a soft bracket, and that's it. Put it down here. And then these are just the domain and ranges of our famous graphs, our toolkit functions. But again, you don't have to memorize this because if you know what the functions look like, then you can very easily identify what your domain and ranges are. A lot of them are all real numbers. These are all real numbers. And then when we're dealing with squares and square roots, then we have a little bit more restriction. The most restriction, I would say, is the reciprocal function, where we have these asymptotes taking place. And then absolute value, what is our domain and range here? Again, if you just look at it visually, you know that, okay, with my range, my minimum is 0, and then we have no maximum. So range is 0, hard bracket, infinity. Domain, no restrictions. We're including all possible x values in the real number system, so we have all real numbers. And then this is just the step-by-step procedure in finding domain and range when you're given a formula function. And so with domain, just like we've done earlier, you want to identify your restrictions and where all of the values are undefined. Those are going to be excluded. And then with the range, you want to figure out, okay, after we identified all of your X values, what are all of the possible Y values that can be computed from that? And then that would be your range. So now let's look at these three examples and compute both the domain and range for each one of them. It also does very much help to know your toolkit functions and know the sketches of these graphs to determine your domains and ranges as well. So first one, we have a cubic function here. So graphically, you're looking at something like this. Domain. Do we have any restrictions here? No. So our domain is all real numbers. Range. Do we have any restrictions here? No, right? Our x to the third is all real numbers in both cases. Let's go ahead and look at B. Let's look at domain first. Any restrictions? Yeah, what? Our denominator can't be 0, so we set it equal to 0, and that tells us our x can't be equal to -1. That's our only restriction, which means how would we represent our domain? All values from -infinity up to -1, not including -1, union all values from -1 up to infinity. Our range, we have 2 over x plus 1. So essentially, what's our famous graph here that we're looking at? We're looking at that reciprocal function graph. And we have those x and y axes are our asymptotes. So it's going to look something like this. And so straight off the bat, what can, I mean, we could sort of identify it up here too, but since there's a number in our numerator, what does that tell us? Our y value can never be 0, right? It's impossible for our y value to be 0. Even if we put any single x value in the world here, y will never be computed as 0. Is that our only restriction? Yeah, right? There are no other restrictions. Our y could be anything else, right? All of our y values representing not 0, all of our y values being represented. So how do we write this in terms of interval notation? Negative infinity up to, good, union, 0 to positive infinity, and we're done. And finally, we're on part C, domain. Do we have any restrictions here? We have no fraction, but what do we have? A radical. What can't be underneath the radical? Exactly. So our x plus 4 has to be greater than or equal to 0. It has to be positive or 0. Subtract 4 from both sides. So our domain are all values that are greater than or equal to -4. From a number line standpoint, how do we sketch this out? Well, we put -4 on a number line. It's closed circle. And it's all values greater. So interval notation, it's going to be hard bracket -4 to positive infinity. How do we sketch out this toolkit function? We're looking at square root. So it's going to be like this little curve looking guy from the origin. This is, again, I'm sketching out the famous graphs, not the transformations involved, which we will learn about soon, because there is technically a transformation here. No vertical shifts, so that won't affect our range. But so our range are all possible y values stem from what? Yep, 2. Yep. And we include 0, right? And we're done. That's it. Any questions at all? Yeah.
So there you don't do anything with the number outside
The square root, correct. Yeah. If it was like +4, then this would be moved up 4, and then the range would change our possible y values. But it's a +4 underneath the square root. So this +4 actually represents a horizontal shift 4 units to the left. And so it's not affecting our range at all. Also, yeah, it would affect our domain, but we did our domain technically, so we knew that our smallest value is -4. But if we moved it over, then you can visually see that, oh, okay, yeah, -4 is part of our domain. Yeah, that 2 on the outside just multiplies everything. It's a scale factor. So it's a stretch. It's not, it has no effect on the domain or range. Yeah, good question though. Finally, we're at our second objective for this lesson, which is graphing piecewise functions. And so I'll ask someone to read this little paragraph. Any volunteers? Go for it.
Piecewise function is a function in which more than one formula is used to define the output. Each formula has its own domain, and the domain of the function is the union of all these smaller domains.
Good, thank you. That last sentence is really important. We know that each function has its own domain, but the domain of the piecewise function is the union of all of them put together. So think about it as three separate functions, especially when you're asked to graph it and when you're identifying the domains. But then when you look at the function as a whole, when they're all pieced together, the domain is just the union of all of these. So let's look at a simple example at first. We're only dealing with these two pieces of different functions put together to create a function itself. And we're not even asked to find domain. In this example, we're just asked to find and evaluate at certain input values. So when f is equal to 0, what do we get? Well, x is 0, then we're looking at this top function, right? When x is greater than or equal to 0, well, when it's 0, what do we get? We get x. And our x here is what? Yeah, exactly. Now let's look at f of -1. -1 is a negative number, so it's less than 0. So our output is going to be negative x. And again, our x here is -1, so we're looking at negative times -1, which gives us +1. Good. Now we have f of +1, so we're back to the top one, where we get x, and our x here is 1. And then finally, we have f of 0.5, which is still the top because it's a positive value. And we once again are looking at 0.5. Questions at all on this one? No. Right, we have a word problem example. A cell phone company uses the function below to determine the cost C in dollars for G gigabytes of data transfer. C in dollars, that's your output. G gigabytes, that's your input, aka your X value. And we're just asked to find the cost of using 1.5 gigabytes of data and the cost of using 4 gigabytes. So 2 problems in one. We want to find what is C of 1.5, and we want to find what is C of 4. 1.5 falls between 0 and 2. And so they give us our answer straight off the bat. What's our answer for the first one? $25. Good. The second one, we're looking at 4 gigabytes, which is greater than or equal to 2. So we need to use this function over here. And so wherever you see a G, we just have to substitute in 4. And then solve. 4 minus 2 gives you 2. 10 times 2 gives you 20. and 25 plus 20 gives you $45. And you're done. And then this is just the step-by-step procedure in being able to sketch a graph of a piecewise function, where you're essentially just understanding how to graph each piece separately based off of the domains. So these are all of the domains. Between this interval, you're going to have your output to be 25, and then between this range, you're going to have your output to represent this function. And you put it all together. So now we're going to be practicing graphing for a few problems. Example 9 will be our first one. And I'm actually going to bring in a graph to help us out here. So let's look at it separately. First, we're evaluating when x is less than or equal to 1. So we find 1 on our coordinate plane. And that's sort of the breakup between these two separate functions. X squared, thinking back to your toolkit functions, is going to be a parabola that looks like this. And then your 2x plus 1 is a linear function, so it's going to look something like that. And so at less than or equal to 1, what might help you out is just to create a little table off to the right. Maybe I'll color code this, so I'm going to put that line in a different color, put blue. And we're starting out when x is 1, and we're looking at all values smaller. So why don't we do 1, 0, -1, -2. When x is 1, plug that in. 1 squared gives you 1. When x is 0, 0 squared is 0. -1, -1 in parentheses squared is 1. -2 in parentheses squared is 4. And now we can plot this. We have 1, 1, 0, 0, -1, comma 1, -2, comma 4. Yeah, that looks like 5, right? And now we could just extend it. There. Also, maybe color code. Now the second part is this whole 2x plus 1. So once again, create a little table off to the side. You know it's going to be a line, but we're not starting at 1, but it's good to know where the point is at 1. So I'm going to put that first part in red because we don't want to plot this. Plug in 1, 2 times 1 is 2, plus 1 is 3. And then I'm going to put in 2 in blue because we are plotting this. 2 times 2 is 4, plus 1 is 5. I'll put a few more. 3 times 2 is 6, plus 1 is 7. 4 times 2 is 8, plus 1 is 9. So now we have 2, comma 5. 1, 2. I feel like this is 5. And then we have 3, 7. And then 4, 9. And then that 1, 3 is an open circle, which is why I put it in red. Because we want to represent all numbers between 1 and 2 as well. You can only get that if you plotted that red point. And that's it. This is our piecewise function. Any questions on that? Maybe I'll put the divide between the two as a different color. Let's take a look at another example, but now we're dealing with 3 different types of functions. We can be a little more efficient and quicker with this now. So x squared, you know that looks like a parabola. What does your table look like? We're including that 1, so we're going to put in 1 here. And then all values less than 1, so let's do 0, -1, -2. Compute it, you get 1, 0, 1, 4. Plot it. And then sketch it. Okay. Next one, between 1 and 2, for your domain, we just have 3. So the 1 is going to be open at 3, and then to 2, it's going to be closed. Nice little horizontal line there. And then finally, we have the last part, nice linear function when x is greater than 2. So at 2, we have 2. When it's 3, we have 3, 4, we have 4. But the 2's are going to be in red because we're not including them. Open circle. So 2, 2. And then we have 3, 3. That one's we are including, and then 4, 4, 5, 5, 6, 6, so on and so forth. So it's going to look something like this. And that's it. That's our piecewise function. So it's really about breaking them all up and then putting them all together. Any questions on this? No questions? That was the last problem for this section. All right. So the next section is going to be lesson 3.3.